Numerical we will be solving in basic electrical. Find the current flowing through all the resistance using superposition theorem. So the question is asked, find out the current through this resistance and the directions you have to specify using superposition theorem. Superposition theorem means at any time we have to take only one source. If there are now two sources out there, choose any one of the source. If there are three sources, choose any one. Then you have to have three different diagrams. So this circuit, we can draw one of the circuit A with only voltage source. Current source will be replaced by its internal resistance, that is infinity. So we can write here, specify the current as I11. This is I2. But we are drawing for the one circuit 1, I3, 1. Here we can write that I11 is equals to I31, which is equals to 12 volt. This is one's voltage across the node. The resistance here will be 1 plus 5, that is 6. So 2 amperes. The voltage across the 3 is also 12 volts. I21 is equals to 12 by 3, 4 amperes. We can have another circuit where we have a 6 ampere, but the 12 volt will be removed and replaced by its internal resistance, that is 0. So in 0 resistance as a short circuit. And we are giving a current source 6 ampere. Here we will give a name I12, I22, I32. So here we can apply the current division rule. If we apply the current division rule, this current is going this side and this side, and here the current will not go through here. So there the current is 0 and the entire current will be flowing through this. So in one circuit we have resistance 1 ohm, in another path we have a resistance 5 ohm. So when we apply a current division rule, we can write, let us write for I32. Opposite resistance, that is 1, divided by sum of the resistance, that is 6, into total current 6, 1 ampere. The current which is going through 1 ampere is from right to left, but our direction is I12 is from left to right. Therefore we can write I12 with a minus sign. The current through this 1 ohm will be equal to opposite resistance divided by the sum of the resistance. So now we have I1 is equals to I11 plus I12, that is 2 plus I12 is minus 5. Similarly, I2 is I21 plus I22, 4 plus I22 is, here I22 is 0 because no current is flowing through the 3 ohm resistor. So 4 plus 0, 4 ampere. Similarly, I3 is I31 is 2, I32 is 1, 3 ampere. We solve this problem by using superposition theorem. Next, now the problem is in a series RLC circuit. The resistance is given, inductance is given, and a capacitance is there. Connected in series with a single phase AC supply of 230 volts. Frequency is not given. Now a question is asked that, remember the voltage is given in 230 volt, obviously this is a RMS voltage. Now you have been asked the current and that the maximum RMS current. Remember in a RLC circuit, the current will be maximum when Z is minimum. At a minimum value of the Z, the current is maximum. So let us try to solve it. And also the frequency at which this occurs, impedance, and the power factor of the circuit. So here we have the RLC circuit. Let us draw. Now if I get to know what is the value of the Z impedance, so Z is equal to R plus J omega L minus J 1 by omega C, which I can write R plus J omega L minus 1 by omega C. Now the imaginary term, if equated to 0, will get the Z minimum. So directly I can write the Z minimum is R, which is equal to 20 ohms, which also reflects the value of I maximum. The maximum current which will flow is V divided by Z minimum. .5 amperes. Now we said that this term to be equated to 0. This is a case of resonance. So at resonance, the omega L is minus 1 by omega C is equal to 0, which implies omega square is 1 by root LC, or we can write omega is equal to, or L is equal to omega is 2 pi f. So 2 pi f square is equal to 1 by LC, and I can write f is equal to 1 by 2 pi root over of LC. After substituting the value of L and C in this equation, we will get the frequency as 79.57 Hertz. So we get at this frequency, or this, let us say FR, at this frequency resonance occur and the XL value and the XC value match and they cancel each other, and we get a maximum value of the current. Now the question is asked, what is the power factor? So we know that power factor is cos of phi. which also we can rewrite as cos of phi as tan inverse of omega L minus 1 by omega C whole divided by R. This term we know it is 0 for our resonance. So this will be cos of 0, which is equals to 1. So the power factor is 1. Let us go to the next problem. So here the delta connected load is given. A three-phase circuit delta connected load draws a line current of 15 ampere at a lagging power factor of 0.85 from a 400 volt 50 Hz three-phase supply. What is asked? Resistance and the inductance of each phase. That means if I can find Z phase, automatically I can find the R phase and L phase or XL phase. And later on we can look at this problem also. So here in this problem, the supply voltage is given 400 volt 50 Hz AC supply. Obviously this 400 is nothing but your line voltage. So in a delta connected load, the voltage across each phase or the voltage across each load will be phase voltage, and that is also equal to the line voltage. So we can say in delta connected load, phase voltage is equal to line voltage. But the phase current is not the same as the line current. The phase current, you can see that the line current means the line current which is coming from the line, and the phase current is therefore reduced by 1 by root 3 times. The power factor of the load is given to you 0.85. This will help us to find the value of R and L. We know that Z is equal to V phase by I phase. Z phase I can write, and that is nothing but V phase is same as the line voltage. I phase is divided here by root 3. And this value will come out to be 46.118. Now, since the power factor is given to us and Z value, the magnitude is known right now. This is the magnitude part that we get. So we can write Z square is equal to R square plus XL square, or also we can say in phase Z phase square, R phase square, all the terms in phase square we can write. So here we can write 46.118 whole square. R's phase we do not know, XL we do not know. I am not writing this phase every time, let it be like this straight. Now since the value of the power factor, that is cos of phi, is 0.85, I can get the value of the phi, that is 31.78 cos inverse of 0.85. And also we can find tan phi is equal to nearly 0.62, which is equal to XL by R. So instead of XL I can substitute here R square plus 0.62 into R whole square. So that's why we can write here as R square 1 plus 0.62 square. And now we can get the value of R from here, and that value of R, if you substitute, we can get the value of XL here, this much. So here we get the value of R as 39.25 and XL is 24.33. Now if I put the value of here 2 pi f into L is equal to 24.33. So the value of L will be 24.33 divided by 2 pi into 50, because the frequency is 50 Hz. So it will come around 77.47 millihenry. Now the same question is asked here, that if the value of the Z will be remain is same as here. So what is the value of the Z? 46.188. So we can write the Z is nothing but magnitude and the angle phi. So here the value of the Z is 46.188 and the angle it is phi is 31.78. The per phase quantity we know. So now if we have the per phase quantity, we have to find what is the phase voltage. In case of star connection, we find that this phase voltage is different. So this phase voltage is equal to line voltage divided by √3. And the current, line current, will be same as the phase current. So if I know the value of the phase voltage, I know the value of the phase impedance, I can get the value of the phase current. So I can write here that I phase is equal to V phase divided by Z phase. V phase is equal to VL by √3 into Z phase is 46.188 angle 31.78. So this gives me the value here. Instead of VL I can write 400. This gives the value of 5 angle. This angle will go up. It will be minus 31.78 amperes. And we know that the phase current is same as the line current. So that gives me the value of the current of the line current as well as the phase current. Now what is the power consumed by this load? The power is equal to 3 times of phase values, phase voltage, phase current and angle between them. So this will be equals to and the angle between them is minus 31 point. So cos of minus 31 point, the power factor that is already given 0.85. And now if we solve it, we'll get this much watt. So the next problem is that given to us is that in a 6-pole DC motor, the pole is 6. It has got 384 conductors. So conductors are named as Z. Number of poles is P. The useful flux is 30 milliwebers. Flux is always given in milliwebers. So it is actually 0.03 Weber. Speed is given of 800 RPM. The back EMF E1 for lap winding, E2 for wave winding is being asked. If the motor is drawing a current of 10 ampere, that is IA, what is the terminal voltage VT? DC separately excited motor, that is supply is directly connected to the armature. Field winding is separately excited. resistance Ra of armature is 2 ohm for wave wound. So we can have the supply is given directly to the armature. Obviously through a starter here. And the field winding is separately excited. So Vt is the supply voltage. L. This is A and AA. Now back EMF is E, B. Ra is the resistance. Now you have a formula of the back EMF EB is equal to phi Zn P by A whole divided by 60, where P is the number of poles, phi is the flux per pole, Z is the number of conductors, N is the speed. All the terms are given. Now the point is that for a lap winding, A is the number of parallel path is always equal to P. Fixed. So the value of A is 6. Usually the meaning of lap winding is that the Z number of conductors are divided equally in 6 parallel paths. That is why the EMF induced in one series circuit will reduce. So you can find that if you cut these values P and A because they're equal, you will get the value of EB1 as 153.6 volts. Now this is EB1. EB2 is given as phi Zn, here also P by A divided by 60, and for the wave winding the value of A is always 2. Irrespective of the number of poles, A is always 2. So obviously here the number of pole is 6, this is 2, so this is 3. So this is 3 times of the back EMF of the lap winding. That comes out to be 460.8 volts. So now back EMF is given. We can also write the terminal voltage is EB2 plus IaRa, because if we apply the KVL, the terminal voltage is equal to back EMF plus the drop over here. So that is 460.8 plus the current is 10 ampere. So 10 into Ra is 2. So this comes out to be 480.8 volts. So that is how we solve it, all the 4 problems. Thank you. See you in the next video.